So it took about like a minute and a half last time. Still steer awkward.
Who is the deep right there?
Oh, it's working.
All right, good afternoon. Welcome to Colloquium, everyone. This week we have Dr. Tom Lewis from the University of North Carolina at Greensboro, where he is a very recently tenured faculty member as of a couple of weeks ago. Tom's work is in numerical analysis of differential equations, and he did his Ph.D. at University of Tennessee at Knoxville and has been at UNCG ever since 2013. Yeah. So anyway, we're excited to have him with us to talk about numerical methods, which is something I think so far we've not had anyone come to talk about. So thanks.
All right, so thank you for the invitation. Many acquaint students, I apologize. When I was on his committee, I didn't know I actually had the authority not to sign. So it's mostly my fault. All right, but again, thank you for the invitation. I was in Knoxville, we used to have mountains, so I've kind of missed seeing mountains, so it's nice to drive up here today. So yes, I'm going to talk about numerical analysis for a little bit. The main idea, it's kind of a two-part talk. I want to talk about numerical methods that we commonly see, and then the problem of why we actually need analysis. Some things don't work the way we think they should. Usually what you do by hand is guaranteed to fail when you try it on a computer. So we'll give some examples there, and kind of cautionary tale. If nothing else, my sales pitch is analysis. Then we might talk about a little bit of things related to my research. That might be the optimistic goal. All right. So numerical methods. So numerical analysis, it's the study of algorithms you use when you want to numerically approximate a problem. So you take a math problem. Typically they're continuous or infinite in some sense. We need to discretize it, truncate everything, and now try to solve it in finite time on a computer. With the added difficulty of we can't actually do exact arithmetic. We have to round all the numbers to the floating point. So taking these limitations, how can we then construct a method that will work eventually and give us what we hope is the right answer and show that it actually does work? So the main idea is we copy from the theorists. We look at what they've done to solve the problem. Unfortunately, they usually do not give constructive proofs. So they'll say a solution exists and they're done. And now you want to build a car or have some model and you want to know what it actually, if I'm going to make money or not. And there is an answer that I might make money or not. So really the goal is, can I approximate the graph of the solution? Can I get some intuition? Can I show some properties of it's at least always positive? So can we resolve these questions numerically and come up with methods? Usually numerical simulations are used in lieu of an experiment. So I interned at Oak Ridge National Lab for a bit. In 2 years, they ran the big experiment once because it cost too much to turn on the machine, even though they had a whole power facility pretty much to fund it. It's a lot easier to simulate. It's a lot cheaper. Unless you go there where they actually do supercomputing and they're in competition always. But typically it's a lot cheaper to compute. So there's kind of three main issues. One is input error. Can't do much about that. Data error, still can't do much. That's more the statistics end of what we're feeding in. The big one is round off. Computers can only represent finitely many things. They have a finite amount of memory. They can not represent infinity. So once we've truncated things, what's happening? Can we still guarantee some amount of faith in our answers? And then the actual discretization error. To describe the problem, I might need infinite dimensions. I work on differential equations. These are based on limits. Can't do a limit on a computer. So I have to truncate somehow. Have I changed the problem itself? So this is independent of rounding. I can use the exact arithmetic, but I'm not solving the full problem. Did I lose too much? So the main goal is to minimize approximation errors, come up with something reasonable. Really a secondary goal in my mind is efficiency or how much memory usage I have. That's more a computer science idea. So again, that's why I'm focusing on the analysis part. All right. So what happens? Well, in some sense, it's nice if your answer or your method diverges entirely. If it diverges entirely, you probably know it's wrong. The hard one that we're going to show today is there are times it will just converge to the wrong answer that looks believable. So that's where the analysis comes in. How can you rule out this unfortunate case? And then, occasionally you might get the right answer, hopefully, or at least close enough. We use what's called the eyeball norm. If you look at the graph and it looks believable, if you use a thick enough plotting routine, when you draw the graph, if you can't see the difference, it converges. But then usually it works for some problems and not others, even though they're a similar problem. You change one parameter and now everything goes wrong. So that's usually the world we live in here. All right. Another unfortunate part is this last one for like solving nonlinear problems. On your calculator, when you were trying to find x-intercepts or something, it always said zoom in on what you think the intersection point is, and then it would go from there. You have to actually give an initial guess. And the problem there is your answer is only as good as the initial guess. If you give a bad initial guess, it will never converge. If you do the analysis, most of the results say if you start close enough to the right answer, it will converge to the right answer. And it basically says if you're in a ball with the right answer, you're good. And this ball could shrink to 0. So if you can solve the problem and then you plug it in, you're good. So again, that's where the analysis comes in. When are we in this worst case? Usually it's worst case scenario. That doesn't actually happen. But that's why you always had to annoyingly hit that extra button on your calculator. It needed a good initial guess to start. All right. So again, most interesting problems are infinite dimensional in some sense. The first thing we do is we cut off the problem. So instead of taking a limit, instead of dealing with infinity, we cap the problem. We call that the discretization error. How do we go from an infinite problem to a discrete problem? All right. We say it's consistent with the original problem if you were to plug in the exact solution and you only get small errors based on what you truncated that would go away if you just do more work. So consistency means, all right, we cut off the problem, but at least we're close to the right thing. Right. And usually we measure by using the right answer to then judge how far off is the rounded part. All right. So a couple examples of discretization. I guess students don't like taking limits. In calculus, we don't tell them. We really just use difference quotients in real life. So what do you do if you want to approximate a derivative? Let h be a small number, plug it into the difference quotient, and you call that the answer. There's two standard ways to do it. If you let h be positive, you get the forward operator. If you let h be negative, since we do two-sided limits, you get the negative operator. We call those two different things. We don't even worry about it. We just say h is positive. Ends up, those are, if you do the analysis, you get the right answer plus some error that's proportional to h. So as you let h go to 0, you do eventually get the right answer. A better method, the central difference quotient, if you take these two and average them, you get exactly this formula. Now your error is h squared. So you're getting a much better answer as h for h small. And then how do you calculate a second derivative? What do you do in calculus? Oh yeah, you are. I'm talking. I'm not sure. You take the derivative of the derivative. We do the same thing. Plug the difference quotient into the difference quotient. You end up with this nice 3-point formula, and you can actually show the error is h squared again. You get second order accuracy. Usually by averaging, we get slightly better answers. All right, here's an interesting thing. I'm using 3 points to approximate my second derivative. All right, parabolas, I need 3 points to uniquely define a quadratic function. You can show this will always give the right answer for the quadratic function. That makes sense. It actually works for cubics. Typically, you would think you need 4 points to resolve a cubic. If you pick these 3 points correctly with this symmetric form, you will always get the right answer for the second derivative of a cubic function using only 3 points. And the reason is this error is it's proportional, so I hide everything in big O notation. It's based on the fourth derivative of the function. If your fourth derivative is 0, you always get the right answer. So 2 wrongs make a slightly better wrong. All right, another example. So this is one, or derivatives. We could easily calculate derivatives. Why do we need this? We'll see it later for differential equations. Throughout, blue is the first order derivative. Red is the second order derivative. I get to the second part of the talk. What's another one? Let's say we want to calculate this definite integral. We know it doesn't have a closed form for the antiderivative, except this is essentially a normal distribution. We need to be able to integrate this. So we can do it exactly if we use series and then 3, or calc 2, we tell people this is a great answer, except I look at that and I have no idea what's going on. It's an alternating sum, okay. So what do? Well, the easiest way to truncate it, use Riemann sums. This is how we introduce the definite integral. And the easiest one, I guess, is left endpoint. Actually, right endpoint is easier if you're doing a proof. Otherwise, you have an off by 1 index. So instead of the left endpoint, let's say I want to get the answer within 0.001 accuracy. My left endpoint method, I would need 1,800 rectangles to get that amount of accuracy guaranteed. Let's do the trapezoidal rule. What's the trapezoidal rule do? It averages the left and right midpoint, or no. Trapezoidal will be the same now. Midpoint method. Instead of picking the left or right endpoint, pick the one in the middle. Do some averaging. Now I need 19 rectangles to get the same confidence interval around my error. So this is one we have to calculate. If you ever look in the back of the stats book, it has how many tables of this is the probability. It's because they were estimating definite integrals. And we can't evaluate exactly, so we tabulated it. Right. So that was discretization. How could we take, these are some problems we're used to, how do we take it from infinite to finite? Another thing we always talk about in numerical analysis is the idea of stability, which we'll touch on throughout the talk in different places. Really, if you read a textbook, the definition of stability, some of the loose definitions are you solve almost the right problem correctly, which I don't know what that means. Another way to think of it is if I rounded one time and then solved the problem exactly, I would get roughly this much error. Except you don't round once, you round throughout the entire process. Well, stability says all those roundings in the middle that I ignored, they're no worse than if I just rounded once. There is some inherent error I expect from one rounding. Stability says in between doesn't actually matter, it doesn't overaccumulate. So whatever that initial idea was, that's really the right bound to go for. Heuristically, some of the ideas that are related, say I'm solving a differential equation, I know my solution eventually decays to 0 as time goes to infinity. Hopefully my numerical method will do that. Usually we weaken it a little bit and say if my original solution is bounded, I really want numerical methods where my approximation is always bounded. All right. So stability is more of a qualitative feature in some sense. So the need for analysis. So I want to look at a few standard problems where we might use numerical methods and see what happens. A couple of them, it converges to just wrong answer. The other one, which is a little easier to find, but floating point errors accumulate, and then we get wrong answers despite doing everything right. So the first one, we had an oil rig that collapsed a few years ago. Actually 91, I guess more than a few years. Which was a true collapse. It measured on the Richter scale, people lost a lot of money. Awful thing. It was built based on running a professional finite element solver that predicted what the stresses would be, and clearly they were wrong. So they finally went back and did the analysis to decide why did this collapse, where did we mess up on our numerical method. Even though we're using professional software, it looked like a standard problem. Well, the standard problem the code was written for assumes one thing. They were solving one that was slightly different but looks almost the same, and you could still plug it in. Except that almost the same wasn't the same. And what you can actually show is what they solved is the exact right answer for a slightly different problem, where they underestimated by 40%. So what actually happened? You have this rig supported on top of these pillars. The problem they solved is related to what's called a clamp boundary condition. So if you have a plate that's bending that's supported on the exterior or the boundary, clamp says you're holding it tightly. So what do you think of clamp? Really what they had was simply supported. It's just balanced on top, which in the P.D. language it's saying something about the second derivative instead of the first derivative. That's the only change. If you run the problem is you have this curved boundary, so a finite element method immediately makes it a polygon. We can't do circles, we can do polygons. By moving the data inside, that's the same as clamping it, which clamped underestimated by 47%, so eventually this collapsed. They reran it with the right code, and they said this is going to fail at 62 meters. It failed at 65 meters. But this is a very you know, you look at these stress measurements, they're huge numbers. Why would you ever think this is wrong? 40% you're not going to see. All right. Another one, this is maybe less interesting. Let's just solve AX equal to B. I'm going to let A be this matrix. How am I going to pick B? Well, I don't actually want to solve this, so I'm going to say, suppose my answer is 1s. Multiply that by A. Now I know what X or B is. All right, so I'm going to solve it 3 ways. One is I'm going to use MATLAB to find A inverse, because it will let me. And then how do I solve? That's easy, multiply by A inverse. Second one, I'm going to do A/B in MATLAB, which is equivalent to doing Gaussian elimination with row swaps. The way we solve all of this by hand. And then the third time, I'm going to use what's called the QR method, which basically, instead of doing row eliminations the way we're used to, which is formally multiplying by a lower triangular matrix, I'm going to multiply by unitary matrices. Unitary matrices preserve the 2 norm, so things might not blow up the same way. Let's see what happens. All right, I use A inverse for a 50 by 50 matrix. It gives me the right answer. Same with Gaussian elimination. QR method, okay, it's a little bit wrong. These are relative errors. Now I switch to 100 by 100. A inverse is doing really well. Gaussian elimination is giving a very wrong answer. I'm off by roughly 1, which, all right. And then QR method is not much change. 1,000 by 1,000. I knew way more about the answer before I ever used A inverse. I could have picked any vector and done that well. And Gaussian elimination is still giving something that, okay, that's a big error, but if you see the solution, would you know that's a big error? It would look believable. And it's because of these floating point, every time I do a step in rounds, this floating point over accumulates. I'm getting rounded errors that are roughly, I'm off by 1 in the norm. QR is the only one that's working. So, I don't know why I put this. This slide basically says what's happening. If you do Gaussian elimination, which is, for that one, there's no row swaps that would actually occur. So you do Gaussian elimination, you find the relative error. Machine epsilon is basically how well you can resolve floating point numbers. You get this growth factor rho, which is bounded by 2 to the m. So I have an exponential growth factor in my error that I can guarantee that matrix hits the growth factor. It is the example where this less than or equal is equal. I have an exponential term thrown into my calculation, and of course this is going to get wrong answers. But they're also believable answers. All right. The last one, if I want to use, I'm going to, no, I have 2 more. This one, I want to solve a differential equation, initial value problem. So I want to solve u prime is a constant times the function itself. So we know this is an exponential growth or decay, depending on the sign of lambda. Initial value problem, so we know the value at 1. The way the approximation works, you start here. Instead of using the derivative, use a discrete derivative, the forward difference operator, which basically says start here, now move to here. So these little red dots that you may or may not see are just my discrete points where I'm approximating. So you can say, okay, it's following along the curve. I didn't tell you exactly how to do it. It's the explicit Euler method. If you want a better explanation than what I just gave, watch Hidden Figures. It's how they landed the space capsule at the end. When they said, hey, we have this computer, we need to figure out where this is going to land, how can we do this quickly? And the divine inspiration was, we could do this other method. It was the forward Euler method.
By hand.
No, they had the computer at that point. Before they did it by hand. That was.
She did it by hand on the board. Or part of it.
Yeah, she did that. Thankfully, it was not a stiff problem, which we'll talk about in a second. All right, so this is a thing. It's the first method you learn in ODEs. Well, let's say I pick lambda positive, then my solution should decay to 0. All right, if I pick lambda equal to 1, my answer is 10 to the negative 5. No matter what I pick for h, everything seems to be working pretty well. But then you can see as lambda gets bigger, better make h small. H, lambda equal to 100. If I let h equal 0.1, I'm off by 2 to the 100. I have an exponential growth in my error. Or I take it to be 0.01, not a huge difference, I wouldn't think. Do 10 steps instead of 1 step every time. Now my error is 0. There's a major difference. Why is that happening? If you actually check, I did it on that slide, the approximation itself is only bounded if h is less than 2 over lambda. And this is a sharp inequality. If h is barely bigger than 2 over lambda, you get exponential growth. If h is less than 2 over lambda, you get exponential decay. It's really hard to resolve a growth versus a decay. That's why we see these errors blowing up. It's not a continuous either, or you're not just barely wrong. You either get infinity or 0. All right. The last one I want to talk about, this is a little closer to my research. If we want to approximate, it's called the Monge-Ampere problem. It comes up in differential geometry or optimal mass transport. Essentially, it's a PDE in 2D, or it's the determinant of the Hessian matrix. So in 2 dimensions, take these partials, this one, set equal to some function f, so we know f. If f is a positive function, the solution must be a convex function. That's really all we're going to say about it. So use what's called the standard finite difference method. The solution to this problem is actually C infinity, so we're going to, best case scenario, let's test what's happening. Use the standard method that you would learn in numerical methods. On an n by n grid, there are this combinatorial number of algebraic solutions. So what does a finite difference method do? It takes your differential equation, turns it into an algebraic problem. And there are this many roots to that algebra problem. So on a 4x4 grid, I get 16 possible answers. These all are exact answers to the finite difference method. Only one of them is convex. All the others change convexity. But how would you ever resolve this when you try to solve the problem? So that's part of where my research goes. All right. So I actually do now want to introduce the finite difference method, now that you have no faith that it's working. All right. So we'll start with Poisson's equation. So the sum of, oh, there's a typo. You're not allowed to publish my slides anymore. I take my signature back. There's no U there. All right, it's the sum of second order partials.
You do what everybody else does and write on the screen.
Can't afford that one. All right. In 2D, it's just saying we know the second derivative, which should be easy to solve. Just integrate. So not too bad. It's a boundary value problem, though. Instead of saying the initial value problem said I know everything here, I could then move forward in time. Now we're saying I know things at the endpoints. How do I connect the dots? All right. So the finite difference is, there's a theme. Take whatever I had as my derivatives or my differential operators, replace them with difference quotients. We're not going to do anything too creative. What are we really doing? Say I'm solving from this endpoint to this endpoint. I'm picking points in between and saying I want to approximate this function value. In between, I don't know what's happening. I'm only going to resolve it on this mesh, on these finite points. So for this example, I have f of x equal to the negative second derivative. We'll talk about the negative sign later. I would say that's approximately just plugging the different second order difference quotient, which is this 3-point formula. So that's exactly equivalent to a linear algebra problem now. I took my differential equation, turned it into a matrix problem, a linear algebra problem. How does that work? Well, I just look at my first node. My difference quotient says I need these 3 points. I know the boundary value, so I can move this to the right-hand side. And then I have 2 unknowns. Go 1 node to the right, now I have my 3 unknowns. Eventually, I go get to the right endpoint, add these 2 unknowns, move this one to the right. So I have a matrix A times all these unknown values equal to some right-hand side. All right. This matrix is essentially -1, 2, -1. It's tridiagonal, symmetric, positive, definite. It's a nice matrix, has a unique solution. So this will give me some approximation for these y coordinates. All right. It does converge. That convergence, it's actually, the error is roughly h squared, which is part of the stability coming in. Why would I expect h squared is the best I could hope for? Because I said this second order difference operator is h squared error. I'm actually preserving that error even though that was when I knew the function. Now my entire function is the unknown, I still actually preserve that result. And that's a because of this equivalence result we have that says any consistent finite difference method. This is consistent because these derivative approximations are consistent. For a well-posed linear boundary value problem, it's convergent if and only if it's stable. So nothing is over accumulating. I'm staying faithful to this initial, what I would think would be the error. All right. Stability in this context says my solution must be uniformly bounded because any solution to that PD is always uniformly bounded. The bound depends on the function f and the boundary function g. Those two give me a bound. Here I don't get the exact bound. I always gain a constant, but it's still based on the same two source terms. All right. So that's for linear problems. For linear problems, we have this equivalence result, the Lax-Rittmeyer equivalence theorem that says convergent if and only if stable. So I actually work on nonlinear problems, fully nonlinear. So a fully nonlinear problem says, we're really lazy with notation. We also don't like to make decisions. I have some function that depends on the Hessian and the gradient and the function itself and space. So what am I looking for? I'm trying to find some function u of x that if I plug it into this equation, equal holds. All right. Again, red is the Hessian operator or second derivatives. Blue is the first derivative operator. Fully nonlinear from a PDE point of view says it's nonlinear in the second derivatives. Semilinear would be nonlinear, or it's still linear in the second derivatives, might be nonlinear in other terms. All right. Applications, the Monge-Ampere equation, the one we talked about earlier that had multiple solutions for mass transport. The other canonical choice is the Hamilton-Jacobi-Bellman equation, which comes up in stochastic optimal control. So I just wanted to throw as many words as I could at you. It's related to the Hamilton-Jacobi equation, but you'd never know it if you see the two. Hamilton-Jacobi is any fully nonlinear first-order problem, which is a wide class of problems. Hamilton-Jacobi-Bellman has one exact form. So adding the word Bellman very much changes what problem we're looking at. Ends up, I know nothing about F. I probably have no chance here. So we do add a little bit of structure on F. We say F is elliptic. What does elliptic mean in the nonlinear setting? It says I have this monotonicity type condition. I am decreasing with respect to my Hessian operator, which makes no real sense. So you can do a partial ordering. I say the matrix A is bigger than the matrix B if A minus B is symmetric, positive, definite. So all positive values and symmetric. And then if I could plug in those, I have this nice inequality. All right. For linear problems, linear would say I have A inner product. So this is a sum of all mixed partials. If I take the derivative with respect to this argument, the Hessian, I just get the matrix A, the coefficient matrix. So we wrote it in nice compact form. If that is negative semi-definite, or negative positive, not negative positive, negative definite and symmetric, then this would be elliptic. So it's a generalization of this linear result. Right? But really our main assumption is we know some monotonicity with respect to second order derivatives in this strange partial ordering. If you ever hear proper elliptic, that really just adds you're also increasing with respect to this term, the one with no derivatives. Strictly increasing there gives you what's called a comparison principle, which then says uniqueness. So we're going to assume uniqueness for these, but that's a way to guarantee uniqueness. So this problem does have existence of a solution. If you add a little bit more, you get uniqueness. Proper elliptic will have a unique solution. So in one dimension, if you look here, I said I want to find some function u, but I never told you anything about u other than it solves this. Ends up that's not going to happen if you read it literally, which if you're in math, you were trained to read literally. That doesn't work in PDEs. Whenever we write it where you see derivatives, we're lying. Here's what we made. So the way you typically interpret problems, you would think classical solutions. Give me a function u of x. I could plug in x anywhere. I could take two derivatives. I better get f of x. That is the classical sense of a problem. Usually we work on what's called weak solutions when you get to slightly more advanced PDE problems. The idea there is roughly take a smooth function, multiply, integrate by parts. So if you need somebody to teach you integration by parts, Quinn is awesome at it. When you integrate by parts, why would we do this? Now I only have one derivative on my unknown function, and it holds under integration. You can integrate things like the absolute value function. You don't care about corners. So we actually look for weak solutions. They have weak derivatives. So we've actually weakened the idea of one derivative, and now we have some principle that must hold. This is essentially a linear algebra problem when you cut it to finite dimensions. Again, not going to work. Ends up, for fully nonlinear problems, when we say we have existence uniqueness, if we have a comparison principle, the best you can say is our solution is continuous. We can't say anything about derivatives. How in the world do we satisfy this equation if we have no derivatives? So we use what's called a differentiation by parts approach. It allows us to move all derivatives onto some test function. So instead of moving only one derivative, we're going to move everything to the test function. So how do we do this? Well, first we'll look at, to kind of motivate the idea, just calc 1 if you don't mind breaking rules. What does it mean to have a relative max? What happens at a relative max? I have a critical point, right? Derivative 0. And it's also concave down. So second derivative is less than or equal to 0. All right. Now how do I cheat? So, if I had a smooth function, this works. Now I'm going to write my function as the one I care about minus the test function. So informally, I'd say they have the same derivative value, and my second derivatives are ordered. If I could do this, if this is a smooth function, I can plug it into my PDE. So if I had the right answer, I assume when I plug it all in, I get 0, right? Now I don't have the right answer. I have one where there's some relative maxima relationship. Really what it says is when I write it this way, I have a smooth function that touches my graph from above. So my graph might have a corner in it, but my smooth function doesn't. It's touching it from above at some point where I have a maximum. U minus phi is maximized. If f is decreasing in this argument, I would have an inequality going this direction. Gradients are the same. Function value is the same because I touch it at one point. The only thing that changes is by ellipticity, I assume this less than or equal sign. But now this equation makes sense, the boxed equation. This would have to be less than or equal to 0. So we call this a subsolution. It's a function where we can plug this into the PDE and we get this result that makes sense because we're only plugging, all our derivatives are on something we said was smooth. Graphically, we're searching for this function u that we don't really know that solves our problem. Instead of finding u where I can just plug in x and figure out what the output is, I'm going to say, can I define the graph of the solution? If I can define the graph of the solution, really it means I know the solution, right? How do I define the graph? Pick a point, touch it from above. Any smooth function that touches it from above must be a subsolution. When I plug it into my PDE, I must get less than or equal to 0. I can do the same thing from beneath. Touch it at all points from beneath where I can, and I better get greater than or equal to 0. Now, there are problems. What about, at this point here, I have a corner. I can only touch that from above. I can touch it from above by infinitely many functions. There's nothing that will hit it from below. Well, that's actually built into the definition part. So, it basically, when I define these solutions, I'm defining the graph directly. And it's like you're in the dark and you're just trying to figure out, all right, where's the graph? It has to be below this point, must be above this point. Eventually I trace it out in a very slow process. Which gives us this actual definition of a viscosity solution. When we say we satisfy these PDEs, we mean we're finding a viscosity solution. This is the correct interpretation. And what it says is, first I define a subsolution. A subsolution says, this unknown u is my subsolution. If anything that touches it from above, I get less than or equal to 0 when I plug in the one that touches it. Super solution is touch it from below, it must work the other direction. And now if I can find one function u that satisfies both parts 1 and 2, I call that the solution. So I have managed to define a solution to a second order problem, we call it the viscosity solution, without ever talking about derivatives, even though our PDE has 2 derivatives. So this is the way we define solutions. And now for homework, you need to approximate these. I did not know to change advisors when that was literally my homework for several years and ongoing. All right. You actually can carry this over to first order problems. It's the same definition, you just erase the Hessians. So that would be the Hamilton-Jacobi equations. Really, we solve second order problems in similar ways to Hamilton-Jacobi. So, all right, so an example of this. Let's take an easy one. Second derivative squared is equal to 1. I have two classical solutions. One happens, so a concave up function, a concave down function. There are infinitely many C1 functions that would satisfy this definition. And H2, we didn't say what that is. That means it has two weak derivatives. So essentially, under integration, these would make sense. Why do I expect to have all these strange functions that work? I can take a plus or minus sign anytime I take the square root. So I glue together a bunch of concave, convex functions in the right way. I can make sure it's smooth, make sure it has at least one full derivative. That would actually be H2. All these would work. This is what happened on that problem for the Monge-Ampere equation where we had all these multiple false solutions. It's because we were finding things that corresponded to these functions. Using just a standard numerical method here, you're most likely finding these functions, not the right answer. From a viscosity solution point of view, this problem is only elliptic if my original function is convex, which forces it to be U plus. So U plus is the unique viscosity solution. Viscosity solution, that whole definition is in some sense a uniqueness principle, which is still a little bit of a lie because you need a comparison principle to say uniqueness, but it's motivated in that way. All right, so now I've gotten really lazy. Here's my finite difference scheme. So what does this mean? Take the domain you're working on, pick a bunch of x points, so make a grid, and I still want to approximate the unknown y coordinate. And then my scheme says, okay, instead of using f, I'm going to use f hat. F hat means it's discrete now. So this problem, in some sense, needs to be similar to the original. But what am I really doing? I'm trying to find a bunch of unknown y coordinates that satisfy some equation inspired by the original PDE. Okay, well, that's abstract enough. Surely it works. To make this work, if you assume monotonicity of f hat. So the real question is, how do we define f hat? I'm going from a PDE to a finite problem. How do I define this f hat operator, or this function? And the idea is monotonicity. If I have two functions where one is bigger than the other, when I plug them in, I need to get this inequality, which is really kind of looking like that definition of ellipticity, except we call it monotonicity. And it's because it's at the discrete level. All right. And then the famous proof says this does work. Any finite difference method that is consistent, which is going to be consistent, all right. Anything that's monotone and stable, it will converge to the right answer. All right. How did this compare to the linear result? Linear result, we didn't have the word monotone. But then there's one other catch. The linear result was if and only if. The unknown question that I work on in my research is this if and only if or not? And we'll talk about why that matters in a few slides. But this says anything that's monotone with the same so it's almost the linear assumptions except we have the word monotone. Any scheme that satisfies this works, which I've trivialized. How hard could this be to design? It took roughly 20 years. So we knew it would work long before we knew something that actually worked. All right. So go back to our linear problem. We always use linear problem for ideas. Suppose we have a grid function phi greater than or equal to b. What happens? And I'm going to assume they're exactly equal at one point. So this is that whole, and this is local uniform convergence. Everything is locally defined. So locally, they agree at one point, but I also have this ordering. This is like detouching it from above. What happens? Plug into my second order difference quotient. Well, I have equality in the middle, and thankfully these other ones are decreasing. Since I have negative signs here, I get the nice greater than equal sign, and now it's exactly the one I wanted. Why do we always put the negative sign in front of the discrete second order derivative? Really for ellipticity, and also makes it follow this rule. So another way, how can we design a monotone scheme? If it's increasing in the unknown for that equation and decreasing with respect to any other unknown that appears. Those schemes are always monotone, which is really consistent with just a central difference quotient. How can you, all right. This is annoyingly different than what we mean by a monotone matrix, which in matrix form, this operator is also monotone, which means all of the, if you take its inverse, every entry in the inverse matrix is non-negative. So the original matrix has mixed signs. It's positive on the diagonal, negative on the off diagonal. The inverse matrix has all positive signs. Why do we say that is in some sense the opposite relationship? Well, now when you invert this, you can actually preserve inequalities. So this is what would be a maximum principle from PDEs if you're working on classical solution theory. But it's the idea of if I have a function that's greater or equal to 0, now when I invert everything, so when I get rid of the operators, I still have the inequality. It's going the backwards direction. All right. So the linear problem actually has a much more structure that we could use. But monotonicity is this approach. How can we do this for PDEs? Or, well, actually, I'll prove it works first. So it's consistent with differentiation by parts. Suppose I have a function u minus phi, or suppose I want to find u, and u minus phi, any function phi that's smooth, I have a maximum where they agree at some point x naught. All right. That means I can find a local ball where u is greater or equal to phi. If I'm on a local ball, I know monotonicity says f hat for my discrete function is greater or equal to this one. Why is this a subsolution? How do I define my scheme? My scheme says whatever nodes I find here, I must get equal to 0. So when we actually prove convergence for monotone schemes, it is a proof by definition. All right. We prove that, all right, use finite difference, it gives you this solution, the discrete one. Now you find one that touches it, use the viscosity solution definition, and you immediately get it must be a subsolution. Then you can do the same thing if you touch it from above, if you have a local min. So it's really just a proof by definition. So where's my research come in? Why do we care? Or why is this not sufficient? We basically solved all problems. We had a nice result that said convergence. The problem is directional resolution. That one I showed you was monotone because it was nice, everything was aligned, the central difference operator. That's great if you're like doing a Laplacian. Those are a bunch of central difference operators, all the signs work out. The problem is mixed derivatives. If you do mixed derivatives, you're not going to have that nice sign pattern anymore, which immediately breaks monotonicity. So there is a method by Kuo-Trudinger that basically says you have your operator, or you have your PDE in terms of the Hessian. You can do a variable transform, make it a PDE in terms of only central operator or directional derivatives, where I no longer have mixed terms. If I do that PDE result, I now have monotone methods, I can approximate it. What's the problem there? I need directional resolution. I'm on a grid. What if I need this direction? I'm going to need some point up here that's on the grid. My unknown value at this one point is coupled to pretty much every other point in the entire grid. Everything about my definition was local. I want to describe the solution, I described it at one point where I touch it. Any finite difference method that is monotone, this one point is going to be coupled to almost every other point in the domain, which breaks intuition. It also means it's hard to solve. Now my algebra problem is not only nonlinear, it's fully coupled. It is a dense system of equations. So that's where my research comes in. Can we weaken the idea of monotonicity? Because otherwise we have this directional resolution problem. At a high level, what it really means is when you do discrete problems, or if you take just discrete Hessian operators, you can't resolve a saddle point versus a maximum, because you don't know what's happening in these directions you're not seeing. Right? That only happens for low regularity. If you have a smooth function and you take discrete Hessians, it will converge to the exact Hessian, so then it works out. That's because your smooth function already resolves all directions. Now you have a bounded function, or no continuity, or nothing to really work with. You can't guarantee information is moving nicely. So you have this directional problem. Saddle points and maxima look the same at the discrete level, which is really the main hurdle in all of the research. All right. And then I feel like I should at least show I did something. So this is the only slide that talks about my research. The main idea is I want to get rid of monotonicity because this directional resolution problem. I don't want to have everything coupled. I really want to preserve a local structure. So our idea is instead of using monotonicity, we add a high order stabilization. Since we know stability is one of the key elements in any convergence proof, can we propose another idea for stability that gives us a little bit more to work with? The one we typically use is we take our second order problem and we add a fourth order derivative, and then we rescale it by h squared so we're not messing up with the scalings. Can we add a fourth order derivative? Will this smooth things out enough that it'll get rid of these low artifacts, low regularity? All right. All the artifacts we mentioned on the other slide were C1 functions. I want a C2 function. How about I add a fourth derivative? At a high level, that will get rid of these artifacts for me. So can that give us some uniqueness? Then here's a test where we're doing the Monjong-Beer equation, where the exact solution was the absolute value of x. So we mentioned these can have low regularity. Here's a solution to a second order problem. It's the absolute value function. Definitely has a corner. You can see on a low grid or a low resolution, it's definitely over smoothing it. But then as I let h be smaller, it's smoothing out the corner. And then we're still proving it gets there for this problem. Hamilton-Jacobi-Bellman problems are actually much easier, even though they're equivalent. All right. So this is our research. It's called the vanishing moment method, which if you study first order problems, you have the vanishing viscosity method, which is the other definition of viscosity solution, which happens to be equivalent. It says if you want to solve a first order problem, add a second order derivative. As the second order derivative term vanishes, if you put an epsilon in front of it, send epsilon to 0, it converges to the same definition that we just gave. You'll get the exact same solution. These two are equivalent. The open problem is, what about for second order problems? If you had a fourth order problem and then send it away, send epsilon to 0, does it converge to the solution to the second order problem? Can we solve a fourth order problem instead? So we proved it in some cases. Regularly symmetric, Monjong-Beer, we can prove it. For linear problems, we can prove it works. But for in full generality, it's still open. But then numerically, we've tested it for 15 years and it always works. So that's where my actual research was. All right, so numerical methods are used to perform simulations really when experiments would cost too much. The problem, say you have rounding error. We live with rounding error. How do you fix rounding error? You could always increase the precision on your computer. There's really nothing else you can do. At a high level, you can rearrange operations or computations to maybe get a boost where you're not canceling things the wrong way. But that's not looking at the trees, that's looking at every blade of grass to try to fix things. Or you could just increase the precision. You get a slightly better answer, but we know it's wrong. The one we really care about from the analysis point of view typically, or most research, is on the truncation part. Can I take my full problem, truncate it, and still preserve all the features that I need in order to reliably approximate? All right, which is where analysis comes in. Numerical methods, using them blindly, even using professional software and just built-in commands, we got very wrong answers to very easy problems. All right, so there's always this component of analysis that needs to come through. All right. Good methods will preserve some qualitative features of the original problem. And then another main idea, we didn't quite touch on this one, but the other theme in numerical, how do you solve a hard problem? Come up with an easy problem that's close, and then solve the easy problem exactly. Right. That's really the idea of truncation, but you can also extend it to other ideas. This function might be hard. What if I use a polynomial? I like polynomials. I can do calculus with a polynomial all day. Use a polynomial and then solve the problem exactly. Right. That's the whole idea of interpolation in other areas. All right, and then selfishly, UNCG has a doctoral program, and I encourage anybody to apply, especially in-state students. It's great, and we will accept out-of-state. Go to North Carolina. It's a computational math Ph.D., and somehow I was the first numerical analyst. They mostly, historically, worked on discrete computations, so in number theory, other topics, which I was very confused because I was at Tennessee in the Oak Ridge National Lab where they do high-performance computing for everything. And I didn't know there was computing that wasn't high-performance computing. Apparently I was wrong. But then we have hired another numerical analyst and some high-performance people since me. So We have lots of research groups. Really, the main selling point of our department, it's small. We have 22, 23 research faculty, 30 to 50 graduate students at any time. We will know you, for better or worse. So it's kind of the smaller liberal arts field, but a doctoral program, which is unique. Usually doctoral programs are a flagship institution that's much bigger. Ours is still kind of that smaller field. We also have some master's programs. I don't know if I'm allowed to advertise that since you're a master's program, but we do. All right, so like PhD, yeah, you have to know more of this. If you want any information, definitely send me an email or see Quinn, who I guess we should brag about him because he's on our recruitment slide. Teaching business calculus. And everybody looked fully enthralled with that presentation. Thank you.
All right, any questions?